This session with a reproducibility paper by Daniele, Malitesta, Claudio, Pomo, Vito, Anelli, Alberto, Carlo, Maria, Mancino, Tommaso di Noia, Eugenio di Sciascio. The paper is entitled A Novel Evaluation Perspective on GNNs-based Recommender Systems through the Topology of the User Item Graph. Let's leave the stage to Claudio Pomo.
Thank you. Hello everyone, I'm Claudio Pomo from Politecnico di Bari, and today I'm glad to share with you our results about this paper entitled A Novel Evaluation Perspective on Graph Neural Networks-based Recommender System through the Topology of the User Item Graph. Starting with the motivation of this work, we know that recently graph convolutional networks has applied in a collaborative filtering scenario with great results. So we asked ourselves why this kind of model works so well. The answer is twofold. We have the algorithmically reason, because algorithms like GCN and DCCF adapt very well the graph convolutional layer to the collaborative filtering rational, and recent model like Ultra GCN, SVD GCN adopt new strategies, go behind the classical matches passing solution in order to avoid the issue of resmoothing. And the other hand, we have the topological reason. From the machine learning literature, we know that the graph topology play a crucial role in the graph neural networks learning phase. And especially if we revisiting the network topology, if we modify the network topology, it's possible to enhance the learning procedure of this graph collaborative filtering. We also know from the classical literature of collaborative filtering that dataset characteristics have a huge impact on the final recommendation performance, especially if we consider data sparsity or gene index distribution. But we don't know if also the topological nature of the user item data and the new wave of this graph collaborative filtering have the same relation. So it's imperative to unveil if there is some dependencies between these topological properties and the recommendation performance of this graph convolutional collaborative filtering. To answer to this question, we introduce in our analysis three well-known topological characteristics. First of all, we introduce the no degree, and this is related to the concept of the cold start user or item in the recommendation tasks. We also introduce the clustering coefficient, and it is related to the concept of clustering together user or items which receive the same level of preference from the items or for the user perspective, basically. And then we have also the degree assortativity, and this aspect is related to the tendency of the system to put together user or item with the same level of activity in the platform. This work is the consequence of our last reproducibility paper presented at RecSys 2023, and we select from that work three well-known models for the graph collaborative filtering approach: like GCN, DCCF, and SVD GCN. We notice that for this selected graph collaborative filtering, there is an explicit reference to the no degree in their representation formula, in the learning representation formula. However, the clustering coefficient and no degree and the degree assortativity don't have a clear evidence in this formulation. So, two questions arise. Which topological aspect graph-based model can unintentionally capture, and are the topological and classical dataset characteristics influencing the recommendation performance of graph collaborative filtering models? To answer to this question, we propose this explanatory framework, and these are the 8 steps that we adopt for this framework. First of all, we select the models and the characteristics which employ in our investigation. Then we select 3 well-known datasets for the graph collaborative filtering domain: Amazon Book, Gowalla, and Yelp. And for each of these datasets, we generate 600 sub-datasets, adopt a jointly procedure which consider node and edge dropout. And for each of these sub-datasets, we collect the dataset statistics and train those models on this dataset. and evaluate these ones by the matrix of recall at 20. After get the results, we generate the explanation of this connection between dataset characteristics and final performance. And to do this, we adopt a multivariate linear regression model, and we want to assess if the weights of the characteristics are really connected to the final performance and how they impact on this measure. The results are very interesting because, as you can see from these slides, where we plot this bar chart which connected the recall at 20 with the dataset characteristics and topological ones, we note that the linear regression model is good enough for this kind of analysis, since the coefficient of determination is always above 95%, and for the classical dataset characteristics, the first 5 rows in this bar plot chart are connected with the classical latent factor findings, since is very well connected about the dependency between the final recommendation performance and the weights of these characteristics. But if we consider the topological characteristics, and in particular the node degree, we notice a strong and direct connection between this metric and the final recommendation performance. And it's quite easy to understand this because this aspect is directly involved in the formulation of this graphical probability filtering model. Differently from the clustering coefficient, we notice that only the user perspective of these characteristics has a huge impact on the final recommendation performance. And in particular, this is very evident when we consider light GCN and DGCF. But if we consider SVD GCN, this aspect is not so evident, probably because this model adopts an inner user-user and item-item projection, and this aspect is not evident when we consider this kind of metric that adopt a clusterization of the user and items. Last but not least, if we consider the associativity degree, we notice that for all this model, we have a direct dependency for the user perspective of this metric and an inverse dependency about the item perspective. And also this as a mathematical justification, because with the SVD GCN depicted in this slide, we cannot adopt the classical message passing schema, but just a singular value decomposition adaptation, and then we have a graph approach. So probably this aspect affects these metrics, and it's needed to investigate further this aspect in all other classical models which employ message passing schema and model that overcoming this classical approach. Another question is about the characteristics of our dropout strategy, and we ask ourselves if these strategies affect or not the goodness of our explanatory framework. To do this, we plot the probability distribution of node degree, and we notice that in the worst case scenario, node dropout drops many high degree nodes, and on the other hand, edge dropout drops all edges connected to several nodes and thus disconnect them from the graph. So we create 4 different settings for the dataset Gowalla and the model SVD GCN in order to assess if our explanatory framework is good enough for all these kind of conditions. For the setting A, with all the subset dataset generated with no dropout, we notice that the coefficient of determination is very low and statistical significance of the characteristics are poor in terms of confirmation of our findings. But if we consider setting B or setting C with the joint mixture of the node and edge dropout, we notice a higher level of coefficient of determination, and always the dataset characteristics became statistically significant. Finally, if we consider a set with poor edge dropout subset dataset, we have for sure a higher coefficient of determination, but also in this case the statistical significance of characteristics is very poor in terms of findings and information that give us. So to wrap up, we collect this, with this message from this study. The latent factor based model have the same behavior of graph qualitative filtering approach if we consider the classical dataset characteristics, and especially for no degree and clustering coefficient, this model are very connected to these topological features. On the other hand, if we consider the degree of sortativity, we don't have a clear connection between these metrics and the models we consider in our analysis. And in the end, if we aim to go deeper and deeper in this analysis, node and edge dropout jointly adoption is the good choice if we want to become more and more deeper and deeper in this investigation. Thank you.
Thank you, Claudio. Thank you. Unfortunately, we have no time for questions and answers, but hope you can continue the discussion offline. So.